Yeah, I'm based out of the Pacific Forestry Center in Victoria. Greg Smith's the forestry officer that we work together in Beetle Ecology. And there are some collaborators, I guess, on this project as well, more from the modeling aspect. So you might have heard Barry refer to it. So I sort of talked to the modelers pretty early on, because the idea is that this data will do double duty in that it will be able to feed some of the phenology and winter survival models that we already have developed, that Barry's worked on, and also Jacques Renier, who's out of the Laurentian Forestry Center in Quebec, has done some great phenological modeling work with some of the Americans, Jim Powell, Barbara Bentz. The model seemed to work really well in the US. We just need some data to parameterize it for Alberta. So there's a number of factors that limit the range of any species. You know, like distribution of the food source or the host plant in the case of a herbivore, interactions with other species, be they competitors, natural enemies, mutualist facilitators, and climate's a huge one. And we think that climate and weather plays a pretty big role in the distribution, or the historic range, of mountain pine beetle. And Les Safranek, he was the research scientist for decades at Pacific Forestry Center. Probably most people in this room would know his name. Who worked on mountain pine beetle, and he plotted by hand back in the early 70s, I guess, all the infestations recorded by the Forest Insects and Disease Surveys up to 1970. And what he astutely noticed, and so this isn't necessarily presence absence of mountain pine beetle, because you cannot find it when it's at low populations, right? It's really hard. So this is where there was some tree killing ability, maybe not rip roaring, but at least some percolating, killing trees, some type of small outbreaks. Anyways, so what he noticed is this correlated quite well with the -40 isoclime, which also kind of correlates pretty well with where I think the continental divide is. And I think everybody knows -40 is this magic number, and the insects have trouble surviving that no matter how well acclimated they are to the cold, no matter what life stage is facing that -40. It's actually a stumbling point for a number of insects, that -40. But, so I'm not going to harp on it too much, because I'm sure you know it all very well. I just want to point out two things that, like we said, we do have these Rocky Mountains. So it's not like everything on the right of that -40 isocline gets -40, right? So there's areas over here that don't get -40 that the beetle could survive in. Second, I really want to highlight that this shaded area, that has to do with degree days above 5.6 degrees Celsius. And basically, in that shaded area, there's not enough heat sums, there's not enough thermal sums in the summer to get adequate development for the insect, okay? So what that might mean is it's 2-year cycle or 3-year cycle instead, or 1.5-year cycle instead of a nice univoltine 1-year life cycle, okay? So this sort of development part aspect of it is what I'll call, phenology, the timing of certain life cycle events. So I just want to point out that it's not always all about -40. It's also about development in the summer and what happens. And you can see there's been infestations here in the past. So this is the difference between climate and weather, right? You have had, obviously, the beetles here. There's low populations there. They just don't typically do well because the climate over the long term isn't great for them. But you get a few years of good weather, and you can get outbreaks because they are there. All right, so has mountain pine beetle expanded its range? Well, this is where that impressive little movie was supposed to come in. So certainly I'd say at least, in recent history, it seems like we have seen mountain pine beetle move further north and into higher elevations than we have in the past, and eastern spread as well. Now, okay, in southern Alberta, I think, we know it's always kind of popped over the Rocky Mountains, whether that's from, populations west going over, whether there's resident populations there that survive. So I'm going to focus, most of what I talk about, though, is up here. And I'm sure around Prince George and some of this pine and the Pine Pass, the beetle has popped over before. But has it popped way over here before? Well, in recent history, my guess would be no. Has it been there since the last ice age? I don't know. I don't know if it matters. It's so much so for the situation we're facing now, because I think we have what we have there for the reasons that Dan Lux described, that we did get massive flow over. So I guess why did we get this range expansion? Well, we had huge populations in west of the Rocky Mountains and British Columbia. So, you know, in the past, I don't know if there was, since the last ice age, if there's been huge populations, but I don't think we would have had that kind of massive long distance dispersal without these huge populations in British Columbia. And this is a slide I borrowed from Alan Carroll, work that Steve Taylor and Alan did. And basically what they show here is the age structure of the forest over time. And the red bars are the ages that are susceptible to mountain pine beetle. And their point is that at the start of the outbreak, you have 3 times more susceptible pine on the landscape than you did back in 1910. Now, I have no idea if this is a natural age distribution, you know, that you would have saw 2,000 years ago or 4,000 years ago, right? We had big fires in the late 1880s that might have caused this as well. But their point is that there was a smorgasbord set up for mountain pine beetle. And you'll hear people say that we didn't have an epidemic of mountain pine beetle in BC, we had an epidemic of old mature lodgepole pine. So the other contributing factor to the big outbreak in British Columbia we hear is climate change, or at least favorable weather. And this is, Barry showed some of the climatic suitability indexes. There's a number of them, and this is based on the modified Safranek one. And basically it just shows that, you know, in the last 30 years, compared to the 30 years before, we saw an increase like over 50% more extremely suitable habitat for mountain pine beetle in British Columbia. Due to what we think climate change. And so what I want you to look at is where most of this occurred, right? Look in this area here. So there was a big increase in extremely suitable habitat, and also down through here compared to here. And also notice that, you know, east of the Rocky Mountains, like even historically, there's been areas that were more than suitable for mountain pine beetle. It just wasn't there. So it may not just have been that -40, but isoclime, but remember that kind of lined up with a big geographic barrier as well. Right, and if we look at this from the province, which just shows the percentage of pine killed, this is only up to 2009, you can see that where they had the greatest losses, gray being the worst case losses, the greater percentage of pine killed, is exactly in that area where we had the biggest increase recently in extremely suitable habitat, climate, and here as well. And I put an X up here because it's 101 or so around on the Alaskan Highway, and I have a feeling that there's going to be some dark red and gray showing up here once they update the maps, just from what I've seen in the last couple of years. So I guess the question is, well, will mountain pine beetle spread, and is pine in the boreal forest at risk? And there's people that have asked this question long before us. In fact, probably long before any of the grad students or postdocs in this room were born. Furnish and Shank asked it in their 1969 paper, where they discussed what happened in that arboretum in Idaho, where they had a whole bunch of planted pine species, including Banksiana and a whole bunch of exotic pines that were attacked by mountain pine beetle during an outbreak, and they reproduced quite well in the exotics as well as in jack pine. And they actually specifically say, I wonder why it hasn't spread through the hybrid corridor in northern Alberta and into jack pine in the boreal forest. So, so I think that these are sort of the main factors that we need to know that to address this question about mountain pine beetle spread, if pine in the boreal forest is at risk. One is climate, weather, particularly climate. The distribution and abundance of susceptible host, Barry talked some about that, and I think that's really linked to the dispersal abilities of the insect. Because, you know, we touched a bit this morning on how what we think is going on in southeastern BC and the Kootenays, where you have chronic infestations, not huge outbreaks, in a benign climate. That is, we don't think it's climate driving the population dynamics in southeastern BC like it is in some other areas. So, you know, that might be tied to distribution and abundance of the host and the dispersal abilities of the insect. Here you can liken your distribution of pine to maybe the southeast Kootenays, but your topography is really different, and so that would likely affect the dispersal ability of the insect. You know, it might be easier to disperse across the flatland. something like that. So I just throw that out there that I think those two are linked. And also interactions with other species, whether that be other host tree species or predators. But where I think the big overarching one is actually going to be climate. All these other things may contribute, but climate will work at every population level as well. So I think Barry already showed something very similar to this. And it's hard to talk about insects now without considering the potential impact of climate change in the future, because it sort of rewrites the rules. So, and all I want you to see here is, like Barry pointed out, there is potential corridor of climatically suitable habitat that has pine in it. Don't get hung up on this red down here. If there's no pine there, who cares, right? Should cut that out. But yeah, you can see that there is this potential corridor of climatically suitable habitat for spread. And even if you don't have a problem now and in the near term, I would say that it's here to stay and persist. And so in 30 or 50 years, as conditions continue to get better for the beetle, you could have a problem in the future. I'm looking at you because I'm realizing that your glass is half full person, and I should be more positive. Because you talked a lot about being positive, so we'll see if I can figure out something positive. All right. So there's been a lot of focus on overwintering survival or winter mortality, and with good reason, because winter is tough, even in the historic range. Even in a benign climate, winter has been difficult. This just shows cumulative mortality of mountain pine beetle by life stage. It's late star larvae that typically overwinter with the 1-year life cycle. The steepest part of the curve, where you get most mortality, even in the historic range, is during the winter, right? So in a normal year, you get at least 40% mortality in the winter, either through direct effects of the cold, but also a lot through desiccation and drying of the tree. That probably doesn't get enough credit. So we know that the different life stages of mountain pine beetle vary in their cold tolerance. Some of these numbers we actually know from experimental work. A lot of them, some of them we only know from sort of modeling work. There's a ton of work to be done here, and also about the role of acclimation and preconditioning that leads up to that. But what I really want to stress is going back to that shaded area on the map that Les Safranek did, 40 years ago, and point out that it's not just about that winter cold, it's also about your development during the summer. And how you develop in the summer and what stage you get to determines what stage you enter the winter. And the different life stages have different cold tolerances. So phenology and that development is really coupled with overwintering survival. We have a survival model, we have a phenology model, and right now I think Barry and Jacques are getting to the point where they want to actually try and couple those two, because we realize how related they are. Yeah. So I guess the question I'm working on is, how will climate and mountain pine beetle phenology interact in the new habitat and affect population success? So on a more detailed level, we really want to quantify mountain pine beetle development and survival as it relates to temperature. And this is at quite a really fine spatial scale. So Barry's worked before with the coarse spatial scale data of weather stations. And at a regional level, it might do well. But one thing he's harped on is that we need much finer scale stuff. So, under the bark within a tree, we want to look at development and relate that to the thermal sums that those developing insects are actually facing. And then this was touched on this morning too, that there's some work with UMBC and UBC that has shown that mountain pine beetle that has moved into areas that have only become recently climatically suitable for the beetle. So areas perhaps where the populations of lodgepole pine have not had a long coevolutionary history with the beetle may not be well adapted or have good defenses against the beetle. They have a different chemistry. They're still lodgepole pine, but their chemical defenses and stuff are different. So we wanted to look at mountain pine beetle reproductive success and attack characteristics related to temperature, but also geographic variation in that. And then, like I said, the idea is that this data will also sort of do double duty in that it can be used to parameterize some of these models we already have that are working quite well in the US for northern Alberta and even BC. And I guess then I stopped. But so the point we are right now in the lab is we have, it's kind of an exciting time, and that we have a lot of our samples processed and stuff, but we don't have, I don't have the data analyzed yet. Greg's still working on the weather data, and I'm still working on cleaning some of the insect data, so I don't have a ton of results to show you. So I'll just talk a little bit about what we did, and just give you a little bit of preliminary stuff, and then I guess hopefully next year. Well, we'll have the results before then. But so I established 18 research sites in three different regions. Down here we have a few sites down in Princeton, southern BC, high elevation and low elevation, northwestern Smithers. Terrace is a real anomaly. It's quite a weird stuff, and logical pines growing with terrace, and there's definitely some cool things going on there. Don't have a lot to do with climate. I think it has a lot to do more with the site effects on the host, but that's probably another story. Fort St. John, like I said, we got those sites for 1 year, and then we have to go up to Fort Nelson now to get sites that aren't totally schwacked. So all the trees were attacked. There's no green trees left there that we can, anyways. And then Grand Prairie and Fox Creek. We also put some ambient temperature stations over in Saskatchewan. Just gives you a sort of a comparison of the sites by elevation and where they are. I actually wanted some in Caribou-Chilcotin, kind of like in the heart of the historic range of mountain pine beetle in BC, but there was no active populations then, so that's why I ended up down in southern BC and over in Smithers. Basically had to go where you could still get active populations. Now the gray bars basically is an adjustment because these sites are at different latitudes, right? So according to this rule of Hopkins biology climatic rule, you just add 120 meters in elevation for every 1 degree north you move. So pretty interesting. You can see they're actually very similar with the adjustment in terms of elevation. And I'm just going to give a little quick thing on the methods. We identified really new attacks. So when the beetles were just entering, this is just a series of beetle butts because they're fun to look at. And you can see they're just starting out there. There was a second beetle, but I accidentally smushed it. So we were pretty good. This obviously offered, there were some challenges in this, both biologically and logistically, being out there right when the trees were being attacked. Working at different areas, but we did pretty well, especially in 2010. And this is important because we want to know from these insects now that they're going to go in there and lay eggs. If I hadn't killed me, we want to know the thermal sums that they're being exposed to throughout their entire life cycle. So that's why we wanted to know when these trees were being attacked. We put temperature probes under the bark. We also set up some ambient stations. And then we went back over periodically over the life cycle, the 1 year life cycle of the beetle, and we picked out larvae, measured head capsules, which is what Ryan, one of the co-op students, was doing. So that allows us to put them into Instar. Yeah, so I guess I won't go into anything more about that, but this is like thousands and thousands of larvae. From different sample times and 18 different sites. We also put some emergence traps on just so we could capture emerging insects to get actual brood productivity. So we put those on in June in northern Alberta. And then we measured some other attack characteristics like attack starts and stuff. We put, some people have mentioned to me that they've seen these weird trees out in the forest all flagged up with chicken wire loosely wrapped around them. Yeah, that's me. And the reason is, you can see here, the chicken wire went up to about here. Dominique's pulled it off so she can put on the emergence trap. This right here is woodpeckering. If we hadn't put this on, we would have come back after putting all that effort into these trees and had nothing. And we were out, I was out in the first week of March last year, when it was minus 24 in Alberta, and just to see what it was like. And make sure that this chicken wire is loose enough that it wasn't actually packing snow. So there was no thermal effect, really, I don't think, of having this chicken wire on there. All right, so like I said, I don't really have many results, so I'm just going to show you a bit. And I mean, the main thing I want to do is couple that development data with the temperature data, and that will be forthcoming soon. So in 2010, I think the flight in this area was mid-July. Dan said from his graph, he showed when it was in 2011, I think it was about 3 to 4 weeks later. I had it to early to mid-August. he had 2 peaks. I found more just one big extended thing, but you get a cool day in there and trout catches can drop. In 2010, the interesting thing is we did have trees attacked. I'll call them early attacks, but really they were attacked during that main fight in mid-July. And then we had some late attacks, trees attacked in August. And I'll show you some photos and why that was sort of exciting to us in that year. 2011, all the trees were sort of attacked basically at the same time, once during that late flight period. And the flight was late everywhere in BC, as you can see. So this just shows an example of we're sampling larvae from the bottom of some galleries around the temperature probes. And so this is a 2010 attack, so this we're sampling it right before we go into the winter in September 2010. So this tree would have been attacked mid-July, and you can just see how much further advanced it is in terms of how big the larvae were from the size of the galleries, how much more developed the fungus was. That would totally affect the moisture content of this tree, and we did measure that at all the sample times. Versus a late attack tree from that same site that was attacked a few weeks later, let's say mid-August, where the larvae were much smaller. You still have pink juicy phloem here. What's going to be really interesting to see is how well those insects caught up with each other, and if they did, and if they have differing survival through the winter. I thought I should throw up some temperature data just to show that we have it and are working on it. And this just shows Musrow, sort of the winter temperatures. And the reason I picked this one is, if you remember in the fall of 2010, November 23rd, there was that really cold snap where it went down to -30, and there was some hoopla about, oh, maybe that was enough to do in the beetles, and then, oh my god, it actually wasn't. But we had that kind of rare extreme cold event in the fall. And the reason this probably wasn't enough, -30 in the end of November, to do them in, is if you look here, there were some sub-zero temperatures right before there. So they probably acquired their cold hardiness here. And once they get that, they're good to go. That is, drop away, it doesn't matter how fast it goes, they're good. Now, we know that if they get like -5 for 2 weeks, they'll get their maximum cold hardiness. What we don't know is we don't know the minimum required to get the maximum cold hardiness. We don't know if 1 week at -5 is good enough, or -3 for 1 week or 2 weeks, or that kind of things, before they would be susceptible to extreme cold events. And same reverse process in the spring. Smithers. All right. Okay. And then this just shows the cool summer we had, Musrow, from June this past year. 15 degrees is sort of like a soft threshold for emergence, 19 soft threshold for flight, although they prefer 22 degrees better before they fly. North and south aspect of the tree and solid and dotted lines. And what you see here is, no wonder they didn't fly to mid-August. Good God, it was too cold to come out. That was interesting, but I'm not going to tell you about that because I don't have time. But mean Pronotowoods, size is tied to fecundity, survivalship, that kind of thing. This is from our emergence traps, and all you want to see here is that west or east of the Rocky Mountains, they weren't suffering any from that point of view. Sex ratios, Barry touched on this morning. And all I'll say here is these lower numbers means more females. You have more females when the population's stressed because they're larger, they survive better, and you would invest more in females when times are tough, right? Because they're going to keep the population going. Males will mate with more than one female. Don't believe that monogamous stuff you hear about mountain pine beetle. So what we see here with higher males in these populations, to me, would say these populations are not stressed. If we take more females as an indication of stress. Mean number of beetles per emergence traps. This needs to be converted to density because we actually measured the density of these traps, but haven't got there yet. Again, this is traps that are about 15 centimeters wide by 45 centimeters high. What this means is there's a crap load of beetles here. Again, not doing too bad, especially for St. John. If you converted this number, I think you have to multiply that by like 15 to get number of beetles per meter squared. And we know 60 attacks per square meter is a good number for getting overcoming tree defenses and not getting a whole bunch of intraspecific competition. So that's huge numbers. Oh, final thing. Keith asked me to touch on future research. I'll just talk about what I think in my lab we'll be doing. I should quickly introduce, this is Greg Smith. He's the forestry officer that I work with. And also Vince Waring is a pool technician that has been on many trips with me to Alberta. And that sometimes helps us out mostly in the field. So where I think we'll go in the future is we'll still focus on some of this overwintering survival, especially in terms of temperature, but also in terms of the stage that went into the winter, because we only have 1 year of data for the overwintering survival stuff. We'll have 2 years of development data. And in the future, I'd like to do some cold tolerance work. So actually figure out the parameters around that cold acclimation, like I was saying, like the minimum required to get the maximum cold tolerance. And where this might come into play is Dan had talked about the holding zone in Alberta, you know, and he said what we do there is we try to keep the population static until Mother Nature can help us out. Well, what do you need from Mother Nature to help you out? Like with this kind of work, we could actually maybe start to quantify what type of rare event you would need, because we know what would be required to kill, say, a certain percentage of the population. Well, if it goes from +10 down to -15 in this amount of time, we know these many dies, or -20 or -25. And we can sort of start to quantify what type of rare event would be needed to kill them off, those early or late season events, same with the spring. And then you could say, you know, how likely is that to happen? I mean, these shoulder season rare events are by their very nature and definition rare. So lots of people to thank, Les Safranek, for great discussions. Lots of students that have helped out and processed a lot of samples and stared some cougars down in the field. We've had lots of volunteers from other labs in the building come out in the field as well. And the companies for research on their sites, and of course all the funding institutes, FRI, and the provinces, Alberta, Saskatchewan, Manitoba, and Ontario through Surge and Forest Protection Limited, as well as some Natural Resources Canada funding as well.